Now coming to next topic, that is capacitors. Now we should know what exactly is capacitor. What is the purpose of capacitor? Then we will see how that purpose is achieved, right? And even before that, we will see what happens to a conductor when it is kept in an electric field. So let's start with that. That is, what happens when a conductor is inside or is kept in an electric field. Let's study that. So what happens here is, uh, let's say you have two plates. We have already seen this, right? Let's say one of them is positively charged and the other one is negatively charged. So what happens here? There will be an electric field set up here, right? Let's say that electric field is nothing but represented by uh, E naught. That is the electric field. And what will be the direction of this electric field? It will be from positive to negative. Now let's introduce, so there is an electric field there. Now let's introduce a conductor inside this. Let's say this is a conductor which is kept inside the, or in between two plates. So that's why it is kept in an electric field. Now, in this scenario, we say that the net electric field intensity in the interior of a conductor is zero. So what is the reason for that? Reason for that is that when conductor is placed in an electric field, the charge, that is obviously the free electrons, drift towards the positive plate, leaving the positive core behind. What does that mean? So see here, there is a positive charge here, and there will be free charge carriers inside this conductor as well. So out of those, most of the charges will get attracted towards this positive plate. So the electrically negative charges, right, that is nothing but the free electrons, will get attracted towards this side. And obviously when an electron from the right side will move towards the left side, then the right side will generate or will develop a positive side or a positive charge. Now, due to these positive charges, right, which you are seeing now, there is a polarity developed inside the conductor. One end is positive and the other end is negative. So that means what? In addition to the outer electric field, right, which what is the direction of outer electric field? From the positive to negative. So this is the direction of outer electric field. And in addition to this, so the outer electric field was there due to the charges, positive and negative plates. Now the same charge separation is inside the conductor as well, and due to that there will be a field inside the conductor as well, from positive to negative. And what do we see here? These electric field which you are seeing here is actually in the direction opposite to the direction of the outer field, right? Okay, so it is due to this field which is set up in the outer direction that we have net electric field equal to 0. So the E net inside the conductor will be equal to 0. Obviously, because there is an interior or internal electric field which is, you can say, is equal and opposite to the outermost field. So the net field inside is 0. So that is the one thing, that is net electric field inside the conductor. This is when the conductor is placed. Now this is not about the shell which we have seen earlier. It's not shell. Any conductor inside an electric field will have 0 electric field inside it, right? That is in the interior or in the bulk of the material or that conductor, the total or the net electric field will be equal to 0. This is not same as the one which we have concluded in the previous video, where I explained that the conductors, that is the field due to the conductor or a thin spherical shell inside the conductor is 0. That is a different thing. This is a different thing. Okay, so that is the first behavior, right? Second is, if you have a conductor of any irregular shape as well, the electric field just uh, outside the charge conductor, obviously the conductor is a charge conductor, so just outside the charge conductor, let's say for example you are finding electric field at this point, right? So at this point the electric field is perpendicular to the surface of the conductor, right? The electric field just outside the surface is perpendicular to the surface. That means the lines of forces which will be coming out of the surface will be always perpendicular to the surface. And we have already seen actually how or why is it like that. Suppose uh, this is the direction of normal to the surface. So we are saying that electric field will be in that direction. Now, how to prove that? Let's say the direction is not that and direction is somewhere over here. Let's say the direction of electric field is this. This is our assumption. Now, if this is the direction of electric field, it will have two components. One component along the perpendicular, which will be equals to E sine theta, and one component along the surface, which will be E cos theta. Or basically, there will be a component of the electric field along the surface, right? That will be, say, E cos theta. So this is along the tangent or along the surface. Now, because it is along the surface, it will tend to accelerate, because electric field will give you what? Due to that electric field, there is a force. What is that force? Force is equals to QE. So if there is a component of the electric field along the surface, there will be a component of this force as well along the surface, right? And that will tend to accelerate because there is a force, due to force there will be an acceleration, and the charge will accelerate on the surface, and if that happens it will lead to a surface current, that is current due to flow of charge on the surface. But when we are studying electrostatics, that is charges which are stationary or not being accelerated, so here there should not be any concept of surface current as well. And if that is there, that means this theta has to be such that cos theta is 0. That is possible only if theta is equals to 90 degree. That means E is always perpendicular to the surface when it is coming out of the surface, right? So that is the second behavior. Now the third behavior, net charge in the interior of the conductor is 0, right? So if there is a conductor like this, the charges may separate. There may be charge separation, but the net charge will be equal to not E net, the charge, total charge. Inside the surface will be always 0, right? And this is again proved by the Gauss theorem as well itself. So this is equivalent to Gauss uh, theorem proof which we have done, right? So net electric field inside a conductor, whether it is hollow or not, is 0. That is a different thing. Net charge inside is 0. That is a different thing. Okay, so that was the third. That was the third behavior or third property, you can say. And that means what? Charges are always on the surface. Charges always reside on the surface of a conductor. There won't be any charge inside and outside the conductor, right? So whatever extra charge you give to a conductor, right, that charge will spread only on the surface. Okay, uh, yeah, that's about the fourth property. Next, electric potential is constant for the entire conductor. Now this is again very important. Electric potential is constant for the entire conductor. Okay, we know what is dV. dV is minus E dot dr. I hope you still remember this. And since E equals to 0 inside or in the interior of the conductor, so that means dV will also be equal to 0. This means V is equals to constant, right? So electric potential is constant for the entire conductor. It doesn't change for the conductor. The potential of a conductor is constant. You go to any point in that conductor, any place in that conductor, it will be constant. So charge inside is 0, charge is only on the surface, potential is constant, electric field inside the conductor is 0. So these are few properties. And one last property about the charge distribution. So the surface charge distribution may be different at different points. What is a charge distribution? It is, we know that this will be equals to Q divided by S. So every conductor is an equipotential volume, right? That is the potential will be equal inside the or in the conductor. It will be equal at every point, right? So it's not just an equipotential surface, it is equipotential volume as well. So you have to remember that. Now if your conductor is like this, let's say like this, so it is clearly visible that there are portions where the surface area is very small and there are portions where surface area is more, right? But the charge distribution will be like this. So obviously it means what? There will be more charge because the volume, the potential has to be same. And potential is what? Potential is kq divided by r. That means potential is directly proportional to q. So here charge has to be less. If the, as you can see here, right? Here charge has to be less and here charge has to be more, right? So that's why in this region you will have sigma max, that is maximum charge density, and here sigma will be minimum, that is minimum charge density, or this charge density here will be less. So pointed charge or pointed surfaces, or the surface, or the conductors in which there are a pointed portion, those pointed portion will have maximum charge, or will have maximum sigma, you can say. That is, the density of the charge will be maximum there. Okay, so that is about the capacity, the conductors in an electric field, right? So next, in our next class, we'll be discussing the electrical capacitance. So that we'll do in the next class, and that will be the last topic of this chapter.